Thank you very much. I'm really happy to be here today. It's a great occasion to present these results. The talk connects very well with the previous one. It concerns a research line in which we are trying to rigorously proving certain strong universality features of the Ising model using fermionic Grassmann integrals and implementation of Renormalization Group for the computation of these Grassmann integrals. So it's based on a series of joint works with Vieri Mastropietro, Rafael Greenblatt, who is giving the second part of the talk, and more recently Giovanni Antinucci. So the goal is to review selected results on universality of non-integrable two-dimensional Ising model. The long-term goal would be to prove that the scale limit of any two-dimensional Ising model with ferromagnetic short-range interaction is a minimal CFT model with central charge 1/2 described in terms of free Majorana fermions, as those described in the previous talk. So stated like this conjecture is open, but there are several rigorous results supporting the picture, and I would like to present some today. So to present them, let me start with some notation and definitions. So I'm calling omega a domain of the plane, and omega A its discretization with respect to a square grid with lattice spacing A. So given omega and its discretization omega A, I consider this class of Ising energies. So there is the usual nearest neighbor term. So J is a positive parameter. This summation is over nearest neighbor sites. And this is an additional short-range term which should be thought of as a perturbation of this one. So you should think of this lambda as being a small parameter compared to J. Here, this second summation runs over subsets of omega A. So this sigma capital X is just the product of the spins in X. And Vx is a finite range translation invariant even interaction. So even means that this sum runs over subsets of cardinality 2, 4, 6, say. Finite range means that the allowed axes have diameter smaller than fixed constant times A, say 10 times A. And translation invariant is translation invariant. Here I didn't write boundary terms explicitly, but if you want to consider boundary conditions different from free, you should also include some extra boundary terms corresponding to your favorite boundary conditions. And as usual, the finite volume Gibbs measure with inverse temperature beta, lattice spacing A, this choice of the domain omega, the strength of the additional short-range part lambda, and your favorite boundary condition is e to the minus beta h divided by the partition function.
The big X can have an odd number of elements?
No, even.
Oh, sorry, okay.
2, 4. So you can consider, for instance, just cardinality 2, you have a pair interaction, whatever, but not next to nearest neighbor, say. So the presence of this term breaks integrability, and this is the point. So this, it's well known that at least for lambda small, or say for lambda v ferromagnetic pair interaction, that the model admits high and low temperature phases characterized by unique infinite volume Gibbs measure with no magnetization and exponential decay of correlations, or two pure states corresponding to plus-minus boundary conditions, non-zero magnetization, and exponential decay of truncated correlations. In between, you know or expect, depending on the hypothesis of lambda v, that there is a unique beta c, which will depend on the choice of v and on the strength of lambda, separating the two phases. At that inverse temperature, you expect to have a unique infinite volume Gibbs state with polynomial decay of correlations. And actually, you expect much more. So you expect a very detailed structure of the Gibbs measure, both in infinite and infinite volume. So let me explain some aspects of what you expect. So fix beta equal beta c, fix your domain omega, and rescale the spin variables like this. So the single spin is rescaled with this lattice spacing to the minus 1/8. So this is called the rescaled spin operator. And if you consider the product of two neighboring spins, you subtract the average and rescale by a to the minus 1. This is called the rescaled energy operator. Now take average of product of many of those and send A to 0 after having computed the average in, say, finite volume. So this limit is supposed to exist and satisfy remarkable properties, some of which are the following. So the limit should be independent of lambda up to a finite multiplicative renormalization. So the limit should be certain constant to the power n, certain other constant to the power m, times a universal limit. And this universal limit is expected to be equal to the correlations of the minimal CFT model with central charge 1/2, which are explicitly known. In particular, if you study the limit in two different domains, omega and omega prime, the two limits should be connected by should be one the conformal image of the other under the Riemann mapping of the first domain to the other. Okay, stated like this, this picture that I think is widely accepted is not proven. Actually, it's far from being proven in the generality stated here. However, there are several indications that the picture is correct. First of all, what about lambda equals 0, so the integrable case? So in that case, as already anticipated this morning, and there will be more talks on this, the situation is essentially all solved. It follows from the exact solution, but the full picture requires a lot of results that are much more recent than the classical results in the 50s, 60s, and 70s. So here is a brief review of what is known for in the integrable case. So in that case, the exact solution gives explicit expression for the inverse critical temperature. Onsagra's solution as a simple corollary gives you the asymptotics of the scale limit in infinite plane of energy. This is the result. It's more complicated but doable to compute the scale limit of the spin-spin correlation, which is known since a long time to be this special constant divided distance to the 1/4. To be fair, this result was proven long ago only for xy on the same row, column, or main diagonal. Only much more recently it was proven for x and y in all possible relative positions. While this one is since a long while known for any x and y. And actually the proof of this easily generalizes to the case of n-point energy correlations, in which case the result is this one, is pi to the minus n, the Pfaffian square of this antisymmetric matrix, which is 1 over zi minus zj of diagonal. So here zi is the complex representative of the position of the ith energy insertion. So this is easy to derive, while the counterpart, endpoint counterpart of this is actually pretty hard to derive. Even guessing the right formula was non-trivial. At the end of the 70s, there was a paper by Kadanoff who made a prediction for n spins all on the same line. And only after a few years, the general formula emerged. And it was proven in 2012 by Dubeda and Chelkak, Ongler, and Dizurov, and this is how it looks. It doesn't matter you look at it in detail. This constant A is the 0.7 of the previous slide. And very remarkably, both this formula and the previous one for the correlation actually not only have been now proven in the infinite plane, but even in finite domains. So now, from the works of Smirnov with Chelkak, Ongler, and from the works of Chelkak, Ongler, and Dizurov, it follows that it follows the validity of the scale limit, the analog of this in any finite volume. And in any finite volume, the formula is the conformal image of the one in the half plane. And the one in the half plane is a simple variation of this formula via a simple image rule. Okay, so things are sort of clear for lambda equals 0. What about lambda different from 0? So in that case, we have no exact formula to start with. So if lambda is small, you can hope to do something perturbatively, but as usual, things in this situation in which you are at the critical point, things are not easy to deal with. So one can appeal to multi-scale methods, and actually there is a version of constructive RG machinery that allowed us to prove some aspects of the picture above, also for lambda small. For omega, the full plane, the torus, and the straight cylinder being so far the more sophisticated case we can deal with, we constructed the scale limit of the multipoint energy correlation, so the analog of this Pfaffian square that I mentioned, and we proved that in fact you have a multiplicative constant to the power n times this Pfaffian. And from the technique we developed to control this, other results follow. In particular, we have control of boundary spin and energy correlators. We can compute universal subleading corrections to the critical free energy. And in perspective, we should be able to control the scale limit of the energy correlations in other domains, in particular rectangles, but this is still to be proven. Yes?
Is this using the fermion representation?
Yes, I'm coming to this in the next slide. So a bit of history and details about the approach we follow. So this, as far as I know, at least as far as I'm concerned, this originates from a proposal of Tom Spencer back in 2000, where he published a short paper in which he proposed a concrete way to attack the problem by formulating the partition function and generating function of correlations for the class of Ising models I mentioned in terms of fermionic phi-4 theory, in a sense, and to study this effective fermionic phi-4 theory via renormalization group method. So this proposal was Tom with Aru Pinson attacked the problem of understanding the two-point energy critical exponent via this technique, and then this later was generalized in various ways that I will try to briefly review. So very roughly speaking, the strategy is as follows. So you start with the solvable case. This is known to be solvable in terms of Pfaffian and determinants, so it can be written as in terms of Gaussian Grassmann integrals. First nice observation, if you take the partition function of the non-integrable model, you can write it exactly at the lattice level, finite volume, finite everything, in terms of non-Gaussian Grassmann integral. So this is an exact representation that uses some standard cluster expansion, not very hard. So this is roughly speaking how it looks. So this is, once again, is an exact formula in which you write partition function or generating function of correlations as the integral of an exponential of a non-quadratic polynomial with respect to a reference Gaussian Grassmann integration involving two different fluctuation fields. So there is one fluctuation field which is massive, that is, it has exponential decaying correlation at the lattice scale for any temperature in a wide interval around the critical point. While phi is a critical field, its propagator, its covariance decays polynomially at the critical point. So once you have this, you can integrate out the massive degrees of freedom. This can be done thanks to certain combinatorial formulas thanks in particular to Battle, Bridges, and Federbush. And you end up with an effective phi-4 model involving only the critical degrees of freedom. And as mentioned in the previous talk, this effective theory involves 2 degrees of freedom per site. And this can be studied via analog of the methods used earlier to study phi-4 models in 2 and 3 dimensions, for instance. And you can iteratively rewrite this in the form of an effective model involving a covariance, a new effective covariance with an ultraviolet cutoff on a much lower momentum scale. So in momentum scale is lower by a factor 2 to the h. H is a negative integer compared to the original one. And the original quartic plus sextic interaction is replaced by an effective one describing effect of fluctuations on larger scales compared to the lattice one. So understanding large distance properties of the model corresponds to understanding the flow of this sequence of effective potentials. And the flow from h to h-1 up to rescaling is the same as the one induced by the Wilsonian RG map that in this context is well known to act on local monomials of these fluctuation fields as multiplication by this eigenvalue. That is 2 to the 2 minus n over 2. So this at the linear level, this Wilsonian RG map is contracting on monomials of order 6 or more, is expanding on quadratic monomials, and is neutral on quartic monomials. Actually, in this very case, due to the fact that we have only two fields at disposal, you cannot form a local quartic term without having derivatives. So effectively, these local quartic terms with derivatives behave like irrelevant terms that contract under iterations of this mapping, and this is what drives the flow to the trivial fixed point, at least provided you control the quadratic terms, which means provided you tune the critical temperature suitably. Okay, so this is a strategy used by Pinson-Spencer to prove universality of the critical exponent of the two-point energy-energy correlation, which is equal to 1, irrespective of lambda. And then this method was generalized in various directions, some of which I will briefly recall here. So immediately after the Pinson-Spencer work, Mastropietro used the same technique to study the energy critical exponent of isotropic Ashkin-Teller. So that's a case in which you have two layers of Ising coupled via quartic interaction of strength lambda, coupling the bond of the first layer with the corresponding bond of the second layer. In that case, the critical exponent is not 1, it's non-universal, it depends on the coupling. And later, that was actually my PhD thesis, we discussed the crossover from a universal behavior in the non-isotropic Ashkin-Teller model, in which you have two layers with slightly different J couplings, to the non-universal behavior you have to the isotropic case. So the crossover is described by either critical exponents that are also non-universal, depend on lambda. And quite remarkably, some years later, Benfatto, Falco, Mastropietro proved that there are special relations, Kadanoff scaling relations that were predicted earlier by Kadanoff and in some other version by Haldane, saying that certain products of critical exponents are equal to 1. So once you know one of them, you can recover all the others. And this kind of relation was later generalized by Benfatto, Falco, Mastropietro, and by myself, Mastropietro, and Toninelli in other contexts, including vertex model and interacting dimer models. Okay, so from this initial proposal of Tom, there was a lot of activity that is still continuing. Back to the case of the Ising model. So in that case, after a few years, in 2012, we generalized the Pinson-Spencer construction to construct the scale limit of all the multipoint energy correlation in the plane, first of all. So we proved exactly this fact that you get prefactor constant to the n times the expected expression from the minimal CFT with c equal 1/2. But our method, unfortunately, was too heavily relying on translation invariance for various technical points. So we were not able to prove the analog in finite domains, not even on the half plane. We were not able to control presence of defects of any kind. So no defects associated with the boundary, and no defects in the bulk. And this prevents, to date, still, these methods to attack the problem of constructing a scale limit of interfaces and even the problem of computing spin-spin correlations, which in a sense are associated with point defects in your domain. So motivated by this, some years ago we started investigating the simplest possible non-translational invariant case, which is this model in cylindrical geometry. So in the cylinder, you have one direction which is translation invariant, the other one which has two flat boundaries, so the easiest thing possible. Even in this case, there were several technical difficulties to be overcome, and that now that they are solved, I think the methods we developed opened the way to attacking more sophisticated cases than those we treated so far. So the result, besides the details, is exactly what I anticipated. So you take a domain that is a cylinders of side L1, L2, periodic in one direction, open in the other, and you fix beta equal beta c of lambda, and there exists a constant z of lambda. Both of them are analytic in lambda and are the same constants that we earlier constructed in the bulk, so they don't depend on the geometry we are considering. And in terms of this parameter, if you compute the scale limit at beta c of the energy-energy correlation, you find z to the n times the expected Pfaffian. This is the analog of the previous formula adapted to the geometry we are now in. So the elements of this antisymmetric matrix are slightly different from those I mentioned before, but are the expected ones. Okay, so a few remarks. So in this theorem, lambda and v can have either signs, so we don't need ferromagnetic interactions, provided lambda is sufficiently small, as we need. Even if it's not formulated like this, the methods of proof also allow us to control the massive scale limit in the temperature direction. So if you take beta to be slightly away from beta c, we can construct the limit, and the limit involves an exponentially decaying propagator, and we can compute the rest mass and all that. Our bounds are uniform in the sizes of the cylinder, so by taking them to infinity in the appropriate way, we can recover the color relations in the half plane, for instance, or those on the torus, or in the infinite plane, sorry. And our proof provides bounds on the speed of convergence as a to 0. And can be generalized in a number of directions, including computation of boundary spin correlations. And in this sense, this connects with the result, a method that is complementary to the one used here, that will be discussed, I think, by Vincent Tassion on Friday in his talk. And also to the computation of universal subleading correction to the critical free energy. So let me spend the last couple of minutes to explain a little bit more about these universal subleading corrections, also because this provides nice open problems even for the integrable case. So here is so a couple of slides about another class of predictions coming from CFT. Fix beta equal beta c, fix your favorite domain, and compute the free energy, say with free boundary conditions at beta c as a power series in the inverse lattice spacing. So there is a bulk term scaling like a to the minus 2 times the area of your domain. A first subleading term scaling like the boundary, and then a second subleading term. These two terms are proportional to functions f of lambda and tau of lambda that in general depend on lambda and on the choice of the finite range interaction. What about the second subleading term? Okay, this term has remarkable universality features, at least at the conjectural level. So if the Euler characteristic of omega, so 2 minus twice the number of handles minus number of boundary components, is different from 0, as is the case for just a finite simply connected domain, Cardi and Peschel predicted that this C omega is logarithmic, and the coefficient is independent of lambda and equal to minus 1 over 12 times the Euler characteristics. This 1 over 12 should be thought of as central charge divided by 6. So from this prefactor, one should be able to read the central charge of the underlying CFT. If the Euler characteristic is 0, like for the cylinder or the torus, then this term, rather than logarithmic, should be order 1, and should be again independent of lambda, but in general should depend on the shape of omega. For instance, if omega is a torus, in which case you don't have this term, but you directly have this C omega, this is supposed to be this combination of Jacobi theta functions computed at e to the minus pi psi, where psi is the aspect ratio of the torus. And if you take the aspect ratio of the torus very large, so if you take a very thin and long torus, the dominant behavior is pi over 12 times psi, and again this 12 should be, 1 over 12 should be central charge divided by 6. So again, this is another way of reading central charge from the partition function of the model. Okay, again, if lambda is equal to 0, there are exact computations telling you that at least for some omega, for some domains, things go as expected. So Ferdinand and Fischer in 69, I think, they computed the second subleading correction to the free energy starting from Onsager solution, and it is exactly what a posteriori was post-dicted by conformal field theory. And if omega is a rectangle, you get the minus 1 over 12 times the log, and this was proved very recently by Hatch in a series of papers. The first one is in 2017, so very, very recent. I'm not aware of earlier proofs. And as far as I know, if you have a generic domain, there is no proof even for the lambda equals 0 case, and I think this would be a nice open problem. What about lambda different from 0? So this is the best we can do so far. So if you take a torus with a very large aspect ratio, we can prove that you take the log of the critical partition function, you subtract the bulk, and what you get is a dominant order, this pi over 12, irrespective of lambda. So we can read, in fact, for this class of Ising models, the central charge from this second subleading correction. This is a paper, this is a result of a few years ago. Now, in view of the methods we developed on the cylinder, I think we are able to compute the full order 1 subleading correction, not necessarily in this limit of large aspect ratio, both for the torus and for the cylinder. It is still to be written down, but there are good hopes that this is doable. The case of general omega is wide open. As I said, even in the case of the integrable model is open. Okay, so I stop here, and I invite Raphael to come to give the second part of the talk, in which probably will enter more in detail on certain technical aspects of the construction.
Maybe we can. Why you should care? Yeah, indeed.
Well, because I mean, even proving that the fixed point is the expected one. I mean, even in the infinite plane, it was not trivial to control the flow, but even more interestingly, there are, in the presence of boundaries or of spin insertion, there is to date no proof that the scale limit is the correct one, is the expected one. So, for instance, an open problem is proof that the spin-spin correlations, even in the infinite plane, at the critical point of an interacting model like this, decay like 1 over distance to the power 1/4. This is, as a mathematical theorem, this is not known. And I mean, technically, there are difficulties in controlling the non-local operators that break translation invariance associated naturally with the presence of 2 insertion of spins. And understanding, for instance, effect of boundaries or in general terms breaking translation invariance are technically required to go towards the direction of confirming that 1/4 is not changed by the presence of interaction as expected at the formal level. Yes?
So in other words, you cannot prove that the model becomes conformal and then identify it with a minimal model at C equals 1 half.
Not yet. I mean,
Because then
we can
everything
prove
would
it.
become clear.
Huh?
Then everything would sort of become clear, right?
Yeah, sure. But typically, it's not in these stories. I mean, it's not like it's very hard to just reduce the proof that you get in the scale limit, the minimal model, to just a single statement. Typically, unfortunately, you have to prove different theorems for different observables, and this is unfortunate. It would be much better to just say, I prove a sort of general meta theorem from which I derive all the correlation functions, but nobody knows how to do it at present.
Are there other questions?
Well, when you couple the two Ising models, the work that you did with Vieri, then you get non-trivial.
Yes.
You get non-trivial exponents.
Yes.
So you have to.
And I think part of the approach here is that some of the techniques carry over. So we're using this trivial case as a testing ground for developing these rigorous RG techniques, which then can carry over to that, where in fact you don't just the result isn't just that it's the same scaling limit, but in fact you have to exactly obtain these things directly from the properties of the RG.
Yeah. Thanks. So this may be in answer to Giuseppe's question before.
And there is
Can you perturb around any model for which you know you have the right scaling limit, or does it need to be exactly solvable?
No, I mean the whole point of this is that
You perturbed around on it.
Yes, we need that. Okay, this is another big thing. So far, rigorous RG methods are mostly, if not completely, restricted to to class of models that can be formulated as perturbations of Gaussian models, Gaussian in some sense. In this case, is fermionic Gaussian. This is very unfortunate, and this is, if you like, against the spirit of the Renormalization Group. But this is again the best we can do so far. Would be very nice to be able, for instance, to understand perturbation theory, for instance, around a minimal model different from C equal 1/2. So take a minimal model with a non-trivial central charge between 1/2 and 1, and use that as the starting point of your perturbation theory in the spirit of conformal perturbation theory. Nobody knows how to do this rigorously. Rigorous means controlling the errors you do when you have finite lattice and how fast they go to zero.
So you think even if you take some of the other exactly solvable models that Baxter does, which correspond to those classes, you can't control.
So you need a pretty strong instance of exact solvability. So it's not typically it's not enough. You have beta answer solvability, and again, that would be very nice to push the methods we have now towards that direction. But this is
okay. Well, thank you very much for this talk.